The next unit is entitled Waves and Particles. Light has been described both as a particle and as a wave. Newton first talked about light as being particles. And with his explanation, he could talk about reflection, refraction, and dispersion. He could explain all of them by assuming light was a particle. Later on, though, Thomas Young and others found that a wave-like description was the only way, here's the wave, to explain diffraction. James Clerk Maxwell, in his seminal Maxwell's equations, then described light as perpendicular magnetic and electric fields moving along as a wave. So at that point people thought, there we go, it's a wave. Albert Einstein then came in and he used the particle model to describe the photoelectric effect. Arthur Compton then used the particle model to explain the frequency shift of unscattered photons off of electrons. So what is it? Physicists love symmetry. So light has been described as being both a wave and a particle. So once electrons were discovered and well understood that they were particles, what could physicists be thinking about? Physicists love symmetry. So light has been described as being both a wave and a particle. So once electrons were discovered and well understood that they were particles, what could physicists be thinking about? So if light can be described both as waves and particles, Louis de Broglie in 1924 proposed that particles could be described as waves, and the wavelength would equal h Planck's constant over its momentum. This is the exact same equation that Compton used to determine the momentum of a photon. So all particles, and by extension objects like baseballs and bowling balls, all have a de Broglie wavelength associated with their motion. But remember, h is so very, very tiny, and the momentum of a basketball is very, very, very large compared to the Planck's constant. So the wavelength associated with large objects is vanishingly small. It is very, very, very tiny. Therefore, the wavelength of macro objects like basketballs, human beings, baseballs, etc. really is so tiny you can't notice it. What's the use of this description? Let's take small particles like electrons. Their wavelengths, their de Broglie wavelengths, are about 10 to the minus 10th meters, and that's roughly the size of the atom. So once that happens, you could expect that they could experience wave-like effects like diffraction and interference, just like light does. So de Broglie proposed an interference experiment be set up with crystals and electrons to validate the theory. For some reason, no one tried until decades later. In 1927, Clinton Davison and Lester Germer were studying how electrons bounce off of a nickel surface. During the experiment, there was an accident. The accident resulted in the scarring of the nickel surface, making it act like a three-dimensional diffraction grating. They were startled to find an interference pattern in the scattering. Electrons were diffracting just like they were waves. This was the first experimental proof of de Broglie's hypothesis, and it came by an accident, just like X-rays were discovered by accident. Some of the most amazing scientific and engineering discoveries were made by accident, such as vulcanized rubber, and of course we just talked about X-rays. After this accident, the two-slit experiment, the double-slit experiment, that showed that light was a wave, as performed by Thomas Young back in 1803, was replicated, but this time they were using electrons instead of light, and the de Broglie wavelength of the electrons was on the same order as the distance between and the width of the two slits. Electrons fired one at a time towards the two slits showed the same interference pattern as light did when they land on a distant screen. This indicates that something like an electron wave must go through both slits at the same time. You cannot imagine a single particle doing that. In other words, it would split up, go through both slits, and then interfere with itself on the other side. However, even as strange as that sounds, the data have been shown over and over again to be valid, and on the next slide we'll show you what that looks like. Here are the photographs of the experiment. The electrons were being fired through a double slit apparatus, and what you see here, this is, for example, photographic film on the other side that gets exposed as the electrons hit it. Okay, so they're firing one at a time. That's underlined there, and I'll underline it again. So after a few seconds, or whatever, a few minutes, you have an electron here, you see one hit there, another here, another here. No real pattern, and it's looking good. You have an electron come through, it hits the screen. A little longer time, you have this. You keep going, and finally you get this pattern, which is exactly like the interference pattern of light waves going through a double slit. So it looks like we have a contradiction here. We're building up one electron at a time, but after we leave it for a long time, we have the interference that we got from light acting as a wave. So we have matter acting as a particle and a wave down at the electron level at the same time.